Hey YouTube, it's Dimitri, and today we're going to talk about stationarity. So this is, I think, the biggest topic in time series. I think this is the most important topic in all of financial modeling, in statistics. I think it's the most misunderstood concept, and yet we keep coming back to this over and over again, and people just think they understand it, but they don't really understand it. And for those of you that know me, time series is kind of my specialty, so this is probably my favorite topic to talk about. I could talk about it for days, months, years. It doesn't really matter. I keep finding more and more interesting information that applies to stationarity. But let's dive on in here and define it, and then we'll talk a little bit more about examples and kind of the implications that you won't necessarily find online in other places unless you were to go gather lots and lots of academic paper and textbooks. But anyways, let's dive on in. Okay, so first off, we're going to start with my favorite textbook, as a lot of you know, Statistical Analysis of Financial Data in S+. It's by Rene Carmona. You can get this now in R, so you can program in R. Again, this book isn't necessarily the most detailed, but it does have a lot of general overviews of things you would use as a quant in finance and other realms. But if you go to page 254 here on time series models, it says the notion of stationarity, which is section 5.3.2, and it states here that stationarity is a crucial property of stochastic processes in time series models. It will be a sine qua non condition for the implementation of most estimation and prediction algorithms. The notion of stationarity can be described in the following manner, and it goes on to the math here. But what you didn't catch here, and you might think, he's a little odd, the sine qua non, I think that's how you pronounce it, is Latin. This means absolutely necessary. Okay, so we're going to define this here at the beginning of the video. I do not care what you are using to model time series. It does not matter if you're using a non-statistical method or a statistical method. It does not matter if you're using OLS. It does not matter if you're using ARIMA. It does not matter what you use. As long as you have time inside of your data and you are using that, you must consider the notion of stationarity, and you must abide by the following rules, okay? That's what we're going to get into here. So often I see people say, oh, Dimitri, I read this paper and it said that I didn't have to do this, I didn't have to do that. And we're going to cover why this occurs. We're going to cover the misinterpretation between academics and practitioners. But let's just go in a little further on defining exactly what stationarity is. Stationarity implies, so specifically here, strong stationarity, which is extremely hard to find. But strong stationarity implies that every single moment is constant over time, okay? So every single moment here. So if you don't know what the moments are statistically, the first moment is your mean, the second moment is your variance, the third moment is your skewness, and the fourth moment is kurtosis. And those are typically the ones that we look at. However, there are more moments. Not every function has more than 4 moments. Not every function has all of these, but if you start looking further down, right, the fifth moment, for example, has to do with the importance of tail versus the center. So it's the mode versus the shoulders and causing the skewness, right? So you can keep going deeper and deeper a lot of times, but that's really, really hard to get. And so a lot of times in practice, we use what we call weak stationarity. Weak stationarity implies that the mean, so the first moment, and the variance, which is the second moment, must be constant. They cannot change with time. Okay, so that notion is fairly simple. It's very straightforward, right? Mean, variance have to be stable. That's it. And then people say, oh, okay, whatever, like I understand it, and they move on. But there's a lot of issues with not having stationarity here, and so we're going to draw out a few examples here, and we're going to talk a little bit about this. So one thing to note is that if you looked at some series, we have 3 types of stationarity processes, especially if you use SAS programming, but there's 3 different types of stationarity. So one, this is going to be called zero mean stationarity. And what this implies is that you have your data here, and of course it's time series, so the x-axis here is going to be time, and then we're going to have what we call y, and your process can deviate here, but in general, right, the mean of this process is 0. This is what we call zero mean stationarity. Again, we're going to imply here, but we're not going to state it. The variance is also constant. Okay, I'm not going to specify what it is, but it's constant. Okay, so the second type of stationarity you're going to see is what we call single mean stationarity. Okay, so what this implies is that you have your data again here, and your processes is going to be somewhere non-zero, but again, your mean is going to be constant, but it's going to have some value. So in this case, let's just say this mean is equal to, say, 5, right? It's constant, it stays at 5, it does not change. Again, here, as most people aren't going to point out here, your variance is going to be constant. It's always constant, okay? This is stationary process here. There's nothing wrong with using this. This is another example of stationarity, just a single mean. All right, now the third type here, we're going to call this trend stationary. So trend stationary. A trend is technically not stationary, okay? So let's say, again, you have some data here, you have time, and you have y, and you have some processes, and we'll say it's a stochastic process, so it must start at 0, and it comes up here, and it goes like this. And so this is not stationary in itself, and the reason being here is that if you were to fit a line on here, right? So for example, if you did an OLS line here, pretend this is straight, the mean here is not going to be constant, okay? The mean here is not stationary. Okay, so why do we say that this could be a stationary process? The reason that we consider this stationary, or it could be stationary, is the sense that as we go back in time now to our other videos that were non-stats videos, you can detrend data. So if we know here that your slope here, we'll call it beta 1, let's say this is equal to, I don't know, 0.75, you can take your data here, called y, and we can divide y by the slope, and you'll end up with a process that would be, again, 0 stationary. So it has a 0 mean. But again here, one of the crucial factors of trend stationarity, again, is that the variance is constant, okay? That does not change. That's something we have to keep implying. So if we look at time series, you can manipulate the data to get it to be stationary. This is going to be the hardest part. This is what we're focusing on a lot of times in creating really solid and deep time series models, is that we need to be able to make things stationary so that we can meet these requirements. So again, this is typically the third one. If you look at SAS, so I've been mentioning SAS a little bit here, but you can do this in R and Python and other languages. When they present these types of stationarity, this is in relation to the ADF test. So the augmented Dickey-Fuller test, they will tell you if it is stationary based on these conditions. If it is, you can do things, for example, detrending here, a trend stationary process, and then you can actually use that to model something as long as you take out the trend. So let's kind of dive on in here for a second on why stationarity is going to be important. So to start off with here, stationarity is important because it helps us predict our beta coefficients. So if we had some model, so again here, we go back just to generic, let's just say we have an OLS regression, you have y is equal to alpha, your intercept term here, plus just beta 1 x1, and then of course we have some error in the model. If you had your data, and let's say you have this data here, you have time, and you have y, and you have some processes, right, and it goes to time here, we'll call this time t, t1, I guess, t0. You start here and you say, okay, this process is stationary, you know, we've detrended it, we know it's going to be constant. The beta term itself will be the same. So this slope, as we've predicted here, this is going to be the beta as your slope, it would continue on in the exact same fashion, okay? One reason, for example, it's difficult to model things such as this, where you have this constant slope, is the fact that this isn't the real world, okay? Stock prices don't trend at a constant slope over time. So having the slope continue on to infinity doesn't make a lot of sense. Again, you won't see a lot of data like this in finance. There might be some areas you would see it, but in general, in the real world, things don't just grow and grow and grow and grow and grow into infinity. There's usually some type of processes that changes it and things that kind of slow it down, and sometimes it declines. You're not going to have this continuous slope here, so it's not really feasible. But let's look at another scenario here where, again, we have t of 0, and you have some processes, let's say, that looks like this, okay? I can tell you this processes is not stationary from looking at it. When you deal with it enough, you'll figure this out. But again, you have this processes here, and so let's say I just take the mean. The mean here is going to look something like, I don't know, like this, okay? So let's say the mean is going to be equal to 0.05. So it has about a 5% slope, give or take. So again, this would be your beta, actually. Okay, so your beta here, your beta 1, let's just say this is equal to 0.05. So your slope is slowly going up over time. Let's just pretend for an instance that we can actually model the differences here with something. But we know this is non-stationary. A, the variance is changing, and B, the mean's changing. But we're going to focus on the mean here. So you estimate this beta that's 0.05, okay? The issue with this is that depending where you were to measure would give you different betas, okay? So as time changes, your beta changes. If you take this period here, right, your beta coefficient would be almost flat. If you took again from this period to this period, now your beta is going to be down. But now you're saying, Dimitri, well, you're cutting it in really small pieces. It doesn't make a lot of sense. Okay, I hear you. Let's unwind for a second here. And let's pretend we take then from, we'll call this t minus 10, and let's say we do it to here, which is t minus 5. It's give or take half the data. Again, if you were to fit this, you would probably fit something like this, right? It's hard to really fit it. It might be similar, even if you had something that was like this. The problem here is that your beta now, so call this beta hat of 1, this might be 0.09. So the issue we're having is the beta is constantly changing. It's hard to predict. And the issue is the errors in this are going to constantly change as well. So it's really hard to get that fit. And so what happens is in the real world, you typically have data that looks like this green data here. And we fit some model to this, and I see this constantly. We have some OLS regression here. So in practice, you'd have this data below, and then you would take somebody who would say, okay, y is equal to, let's say, 5 plus, so this is 5 here, 5 plus 0.05, which is our beta 1 here, times x1 plus our error term, and I think it's great and dandy. And then they end up going and building this model, and they use it for some financial application. And then what happens here, at this point, right, the data does this. Okay, and then what the real problem is the forecast you had, let's say it was something like this. Okay, now the issue is this model is terrible. And the reason being is that your beta is constantly changing. So if you were to add in, again, right, this piece of actual data, our slope would have stayed probably about the same. But when you added in, just say, another year's worth of data here, now the slope technically is going like this. So if you were to refit this, you would end up fitting something more like this. Now we're somewhere in the middle. But you see here, when the mean's constantly changing, it makes it really difficult to model because this beta coefficient here is modeling that slope, and that slope is always changing. And I know what you're thinking here. If you added 1 or 2 data points, your slope would always change. But if you have a solid model, your slopes would change by just a tiny bit. For time series, a lot of times your data is not very large. And then when you add in, say, 6 months or 12 months, it could be a large percentage of the data here. Your slopes are going to change drastically, and I've even seen slopes flop. So you have a positive slope, and then it will end up being a negative slope. So this is really hard to model. It's really basically a scary concept here, and it's really a terrible methodology. This is why stationarity is required, because if you can get a beta that is fairly stable, right, it's always going to change a little bit, but if you can use this where it's a stationary process, and you can use ADF testing, for example, there are other tests as well, but ADF is probably the most common and the most robust. you can have a better process easier. So how do we make this stationary? And let's go through a little bit of the context and the definitions here that a lot of people aren't going to talk about. Okay, so definition-wise, one way to make data stationary is, so again, the Dickey-Fuller or augmented Dickey-Fuller, they've written a bunch of papers on this, and one way to make data stationary is called differencing, okay? The way differencing works is that you take your data, so we say x of time t, and you minus x of time t minus 1, and this is going to be your new x of t, okay? It's pretty simple. You difference all of your series. Again, if you were in Excel, you would have some column like this where you'd have some numbers like 3, 5, 2, 1, 5, and then you'd have your new one here, we'll call it x hat. And again, you're going to miss this data point. It'll be a missing data, so we'll have a period. And then you would do, 5 minus 3 is equal to 2. 2 minus 5 is equal to negative 3. 1 minus 2 is equal to negative 1. 5 minus 1 is equal to 4. Okay? So why is this important? Well, what ends up happening, all right, when you have some series that looks like this, right, there's no way this is stationary. And so if you drew the mean here, your mean would be somewhere like this. And I guess you could say it's constant, but it's not really, because again, if you were to chop this in pieces, this mean would be here. I don't know, this mean would be negative, this mean would be 1. Like, it's not stationary. You can test it if it's actual data, and you'll see that it is. But one important piece here I want to note is that every single movement from point to point, okay, is very small, and it adjusts either up or down. So when you difference data, differencing is one way to make it stationary. If you were to difference this process, you would end up with something like this. And what this is stating here is that we end up now with a zero mean process. Your mean is 0. Your variance, again, will be constant here. But I should note, differencing doesn't always make this occur. You can difference data and not have it be stationary. And if you have large fluctuations, you will never be able to make it stationary. So not every series is going to be stationary or can be made stationary. And that's part of the challenge here with stationarity. But the thing I want to point out here is that when you difference it one time and it becomes the new series, so x hat here is stationary, mathematically you could say x hat is an I0 process. So I stands for integration. So any series that is stationary is going to be I0, okay? But technically we want to know if x is stationary, and we know that x is not stationary. So what we really want to say is that x is an I1 process. So this means if you take x and you difference it, it is now integrated on order 1. So one level of differencing makes it stationary. So a lot of times you'll read papers, you'll see things about people that say we're building non-stationary time series, and people get really excited and they dive in. Cointegration is one of these methods. But to do that, you actually have to have integration to be able to make it stationary. So your process still has to be stationary. So terminology-wise, the level of differencing, and in many cases the level of transformation, so you can use other transformations. It gets a little foggy on this side, but other transformations can make things stationary as well. Differencing is the most common. But if you do that, this is the process. So x here again is not stationary. X is an I1 process. However, the importance is that x can be made stationary through differencing. So technically x is an I1 process, or stated in another way, x hat is an I0 process. So transforming that will make it stationary, and this is required, again, to have stable betas, to have predictable and stable models, and it makes your predictions much more accurate, and they'll actually last for longer periods of time without having to redevelop models. So let's just cover here something that is non-stationary. So one of my favorite examples is HPI. So HPI is the house pricing index here. It is a macro variable. But if you look at the variable itself a lot of times, so again, I'm not going to look it up or anything, but you'll see here, you'll have like, this is like say 2008. So we know this is the crises. you'll have data that's fairly stationary, and then all of a sudden it has these huge drops. Okay? When you difference this, so this, if this is a difference, so we call it diff of HPI, your difference chart will actually look something like this, where you have really nice stationary process here, and then you have this huge drop, and then it's stationary again, and then you have the huge drop again, and then it's stationary again. So the issue with this now, right, is that your mean is not really zero, and then also your variance is not going to be constant. Because you can see here, there's these huge drops, and you can't fix it. Again, you can difference it a second time, so these are called Aitu processes. So if you had, for example, x, and we ended up converting this to x hat, which would be equal to x of t minus x of t minus 1, this would give you x of hat. But then if you wanted to take x hat and you difference that a second time, so again, when we look in Excel, right, we have this column and it has a missing value, and then it has a bunch of numbers. X, we'll call it x bar here. X bar is going to be equal to x hat of t minus x hat of t minus 1. And this will actually give you two missing values to start, and then you'll have values information below. But again, this would be an Aitu process. Do not over difference. I can't stress this enough. You'll actually be able to see this later on, but when you look at autocorrelation and partial autocorrelation functions, so again, I'm jumping ahead of myself here a little bit, but I'm trying to get you guys a little bit excited here and show you some different things. An autocorrelation function and a partial autocorrelation function, so it's an ACF. You want these bars to be below some lines. These are your confidence intervals. But what you'll see is that you'll see, you violate the autocorrelation. But what you'll really see here is you'll see these oscillating bars. Okay. When you have oscillating bars here where it's like it's positive, negative, this is typically a result of over differencing. Okay. So if it's an I1 process and you difference it a second time, then the problem is that it's technically an I1 process, not an I2 process. So if you're over differencing, it'll cause this issue. Again, we're not going to go into a lot of this detail right now, but this is something to keep kind of an eye on and kind of keep in the back of your mind as you're thinking about this. But just to kind of wrap this up here a little bit, because I know I'm starting to ramble, stationarity is very, very important because it has to do with your estimation of your beta coefficients, as we've kind of shown. I'll put a link below as well. There's articles on it, but if you actually do the math, you'll see that the beta coefficient is correlated with time. So as time changes, as we showed in our example, the betas will change a lot. It's not like a little bit because you're adding a little data. It'll change a lot because the series itself is not stationary and you have a lot of random jumps. The implications of stationarity on all time series means that it's very, very difficult, if not impossible, to predict anything. So you can build some model, you can fit it to data, you can overfit it, underfit it, it doesn't really matter. It doesn't matter how you fit it. If you don't have stationarity, it's going to cause a lot of issues with the fact that it's unpredictable, right? That's what it's saying. If the moments aren't predictable, they're not stationary, there's no way for you to predict the future. All right, so one last thing here I'm going to point out is that your equation has to be balanced, okay? So if you have an I0 process on one side of the equation, so this is a Y, and then you have like a beta 1 x1 here, you have your alpha. This piece also has to have the exact same. So if it's I0, this would be an I0. So if you think about this right, say this is Y, and it follows something like this, meaning the mean is constant, the variance is constant, your X might be different. So again, it might have a single mean, you had some intercept term that fixed it. But again, both of these are going to be I0. All right, so let's take another example here. We're going to just blow it up here and kind of show you the issues with this. If Y is going to be I0, so again, this is Y, equals alpha plus beta 1 x1 plus your error. I'm missing all these T's, but, and let's say this side of this is going to be an I1 process, but we did not difference it. We did not make it stationary, okay? So what we're going to say here is that let's say your Y let's just say here that it's something like this, okay? But it's predictable. It's got some constant mean. So this is going to be a single mean stationary process. We'll just say it's I0. And then if you have some x here, and your x actually looks something like this, okay? And let's say if you difference this and this becomes an I1 process. So again, for clarity, let's say this is not stationary. Okay, so we have the single mean process and we have an I1 process, which we did not make stationary. So it's not differenced here. You can see here that the slope of the non-stationary process goes like this, goes up, this one goes up, and then this one goes out, and this one goes out, right? So we have similar shapes, and even here we have a little bit at the end, and again we have a little here at the end. They're similar, so you would say, okay, well, I'm going to regress them. I think it makes a lot of sense, it's all going to be okay. The issue with this is if you start looking, right, these big jumps here are actually going to cause massive issues with prediction. And your betas are going to constantly change when you re-regress this. I know this is like a really close example, but if you were to make like an absurd example, you could see like a process that had like a similar slope. So, I mean, here, let me just do this real quick for you so you can see. If you had another process, let's say, that was non-stationary here, so it goes like this. Right, again, you're still having this same design here where it goes up and the slope goes down. And if you kind of fudge your betas and you do a little bit of fudging here and there, you might be able to get a model here where the p-values are going to be less than 0.05. But the issue with this, again, is that when you have this process and it's not stationary, these jumps inside the data here are actually going to cause terrible predictions. And so when you end up doing a prediction of y, you'll have your typical data point. So we'll compress this and say it looks like this. A lot of times when you go to predict, we'll call this T0. When you add new data to this non-stationarity, the model will refit. Your p-values will become insignificant. And then you'll have, so again, looking at this big jump here, it would predict that your y might do this, okay? It's going to have that really big shift. And even if you were to scale it down, say the beta handled some of it when you added new data, you're still going to have some crazy shift like this, when in reality, your real data perhaps continued like this. So maybe it goes up again, but it kind of stabilizes again. You're going to miss this. And I see this constantly here. So I work a lot with ARIMA models. I work a lot with OLS models in time series. GARCH, for example. You start having these massive errors. So your error prediction essentially will go to infinity in many cases, and they get very large and very cumbersome. And then the conclusion here, which makes no sense, is that ARIMA is terrible, time series sucks, we all hate it, we're not going to use it. And then you end up in a position like those doing credit modeling a lot of times where you refuse to use it because it just doesn't make any sense, okay? So I know it's a little convoluted here. Again, this is kind of a big picture overview of stationarity. We're going to start doing more modeling and detailed analysis as we move forward in the time series set of videos here. But I hope you guys realize stationarity is a requirement of all time series. It doesn't matter what you're using, because what happens is now every time you add a little bit more data, your betas change. And every time you add a little bit more data, then that beta changes. And time series in a lot of ways are not stationary. So we know this, we have to transform them. But again, predicting something that is constant over time, for example, like a zero mean or a single mean or even a trend stationary process, it's easy, right? You can just draw the line on there. It's very intuitive. But again, people don't quite understand that a lot of times. That causes issues when you have data that's kind of bouncing all over the place. And it's very, very hard to predict it if you don't make everything stationary and find things that have true relationships. One thing I didn't cover in this video, which I'll talk about later, is spurious regression. A lot of these cases here where I kind of point out your single mean and your non-stationary series, which was not differenced. When you have these issues, a lot of times they will be correlated and you have really, really good betas, and the p-value is like 0.001, so it's great, it looks awesome. And they'll literally add like 2 months or 3 months, or in the case of CCAR, you add 6 months to do your DFAST, and everything just blows up. Like nothing's related anymore, nothing makes sense. People get frustrated, they don't understand it. But again, having the stationarity kind of grounds us. It gives us something that's easy to predict so that we can provide better, more stable models and predictions. So anyways, I hope you guys found that helpful. Don't forget to like, share, and subscribe. And as always, until next time.